Welcome to another feed scroll generator video for Autodesk Inventor. This is the app that allows you to automatically create beautifully smooth feed screw geometry directly inside Inventor. This is tutorial number 5. Well done if you've made it this far. This time we're looking at how you can use the multiple pitch table editor inside the app to create not just an input pitch and an output pitch for the shaft, but define as many precise bottle pitches as you want along the length of the shaft to create your exact design. Here's what we're going to cover in this video. First, I'll show you a quick overview of how we can use the pitch table editor, how to switch it on and off, and a quick demonstration. And then secondly, a fully worked example of using the pitch table editor to create an exact end result. Actually this result here, where we need the bottle pitches to be exactly this distance as the bottles move along the shaft. And I'll show you how you can achieve this particular goal with the pitch table editor. Okay, so firstly, a quick overview and demonstration of the pitch table editor. I'm going to open up an empty part here and hit generate in the app. And let's head straight to switching on the table editor here. So let's give ourselves enough space. And the place this is accessed is this switch here above in the bottle pitch section. So if I turn this on, then what it's going to do is to open up the pitch table editor for me. Before I make any changes in here, I can accept those changes or cancel them. So let's just say I want to accept those changes here. This will return me to the form, and now you see that we've got a different display of the pitch here in the main form. Instead of having just an inlet and an outlet bottle pitch, we've now got a preview display of the table we're using to define the pitches of the bottles. We can now toggle between both of those. So if I now toggle between the simple start and end pitch and the table, and the preview will update as that happens. You see at the moment, because we didn't make any changes in the table editor, this table actually matches pretty much exactly the default settings that we had for the start and the end pitch anyway, but we can toggle between the two here. So if we just want to edit the bottle pitch table that we've currently got set up, we can hit this button here. If we want to switch it off and on, we can use this one here, if that makes sense. Okay, so I'll head back here and edit the bottle pitch table, and let's see what changes we can make to this. I'm going to just set this transition value to 0 initially so that we can see a bit more clearly exactly what's going on while I explain the settings inside of here. So this table's pretty straightforward in principle here. All it does is allow us to specify as many rows as we want in this table, and for each row in the table we can specify the position along the shaft and a pitch change for that position along the shaft. So we can effectively specify as many pitch changes as we want along the shaft and what position they occur at. Let's come back to this transition column in a moment. But let's say I want another pitch change to be defined on this shaft. You see we've only got one pitch change at 174 millimeters along the shaft, which is in this direction. So at the moment this line is defining the position of the first pitch change, and this distance here from the start of the shaft to here is 174.274 millimeters. Let's add another pitch change in as well. So I can do that several ways. I can hit this button to add a new row at the bottom, or I can right click on the row and add a new row below, either an empty row, or I can copy the values of the existing row. This is probably the easiest way to do it, add row below with copy values. I'll show you both. If I hit this plus button, I get empty cells in the new row, and I've got to enter those values in. So let's hit minus to delete that. But it's obviously quicker for me to right click and add a new row below and copy the values. That will copy the existing values. Now the table's got some nice validation in there. It's not going to update the preview until all of these cells have a valid entry in them. You can see here the value can't be equal to the previous distance, which makes sense. We can't have two pitch changes at the same position. So let's make this say 250. The way I get around this table is I use the arrow keys on my keyboard to move around is the best way to do it. And then what pitch do I want to change to at 250? See, this value is not valid yet, because if I hover over it the pitch has got to be different to the previous pitch, otherwise it's not a pitch change. So I will say that I want here the pitch to change. Let's make this really obvious that we're making a change here. Let's make this 40 for instance, and hit the arrow key on my keyboard. And now, because we've got valid entries for all of these 2 pitch changes here, we get an update of the preview. So you can see the pitch starts at 50 millimeters between each bottle. So these lines are 50 millimeters apart. Then the pitch changes to 100 millimeters, and then at 250 millimeters from the start of the shaft here. So the height of this line will be 250 millimeters from this line. The pitch changes again to 40 millimeters, which in this case, if we just zoom in here, would not really make sense, because our bottle size I think is 50 millimeters. So a pitch of 40 millimeters doesn't really make much sense. But you get the idea here. We can effectively specify any bottle route that we want through as we go along the shaft. Now's a good time to point out that we also see these text readouts showing us what is the pitch between the bottles at this point. This is the pitch to the end of the shaft here. So we can see we've got several pitches of 40. We've got one pitch of 75.73. That's because we've got half the distance is 100 and half of it is 40 or 50. So we don't even have a full pitch of 100 millimeters. If we wanted a full pitch of 100 millimeters, what I would have to do is, maybe if I change that to 150, you see where I'm going with this, 250 minus 150 is 100. So if I hit the arrow key on my keyboard, and if we zoom in again, we can see that we now do have one pitch of exactly 100 millimeters. You notice there the screen keeps zooming in to show the whole table here, or the whole preview. If you don't want that to happen, you can turn off the zoom here. So if I turn that off and make a small change here, 160, and move the arrow key, you'll see that that changes and it doesn't re-zoom to fit to screen. Just an option there. Another way that we can see exactly how many rotations we have for each of these rows in the table. How many rotations do we have at a pitch of 100? Well, if you've been watching with eagle eyes, you might have noticed already that we can see that in the table here already. We can see that we've got rotation of 360 degrees, or one clean shaft rotation at a pitch of 100. If I was to move the position of the second change, let's turn this zoom back on so that it will fit to screen when we change a value. If I was to change the position of the change to pitch of 40, if I was to make that happen later, say 300, and use the arrow key on my keyboard, you can see that now we have 1.5 shaft rotations at a pitch of 100 millimeters. And these values here are read-only, except in one particular specific situation, which is for a dwell shaft, which we cover in the next tutorial, tutorial number 6. But these values are read-only, so I'll only show you how much rotation you have for each of these pitch changes until the next pitch change appears as well. So if we can see we've got a rotation of 1.5 shaft rotations here at 100 millimeters pitch, you can see that relates directly to here to here. This is the pitch of 100, and you can see this line, these vertical lines represent a full rotation of the shaft. So here's where it's starting, that's one rotation, and that's half a rotation there. So we've got 1.5 rotations of the shaft at 100 millimeter bottle pitch. Let's make one more addition, one more shaft bottle pitch change. So let's add a new row at the bottom, added an empty row this time, and let's just say that at 340 millimeters position, I want to change the pitch to something very different again. So let's maybe make that 120 and use the arrow key, and then I'll use a transition value of 0 again. We'll come to this column in a second, and you can see that final change. So we've got 3 pitch changes here. It starts at a pitch of 50 and it changes 3 times. So here's 50, then it changes to 100, then it changes to 40, then it changes to 120. Let's take a look at this transition column. I've kept these all 0 initially just for simplicity, so that we can clearly understand the point at which the pitch is changing is defined by the position and the pitch. But if we enter some different values in here for the transition, you can see that this doesn't have to be a sharp change from, in this case, a pitch of 50 to a pitch of 100. We don't want the bottles to suddenly change their speed of movement. we want that to happen gradually. So let me try putting in a transition value in here of, let's say, 100, and hit the down arrow on my keyboard. So we've now introduced a smooth curve between the pitch of 50mm and the pitch of 100mm. This curve's actually a spline in the sketch that we're seeing here. You can see it's actually centered over this point we chose to change the pitch at. It's actually centered over it, so the pitch is actually going to start changing before our control point and not finish changing until after our control point, which is this point here. So we said we wanted a transition distance of 100mm in the table here, so the pitch now takes 100mm to change from 50 here to 100 up here. It's a spline that controls it, so the transition is nice and smooth. One thing that we need to be really careful of here is perhaps we need to check the actual distance we'll get between the bottles here at this point. You see now that's less than 100. This is because, of course, the pitch doesn't really finish changing to 100mm until we're a bit of a way into the distance between these two bottles. So you have to bear that in mind if you're choosing long, smooth transitions between the pitches. Another thing to note that's important is that these values here, these read-only values for the amount of rotation we have of the shaft for each pitch entry, each row in the table, these are theoretical if you have a transition value of 0. So if we have a smooth curve between the pitches, then the actual amount of time we'll have at each pitch is going to be less than this. You see, we don't have a full 1.5 shaft rotations at a pitch of 100 here, because part of it is taken up by this curve as the bottle speed is reaching the pitch of 100mm. It's going to be less in practice unless the transition value is 0. Okay, let's enter a couple other transition values here. What I can do is I can right click on a transition cell and I can copy the value to all of them. So if I do that, you see now I've entered a transition curve, 100mm transition curve for all of the pitch changes there. And you can see how that changes the effect here. So I can do that, you know, for instance, I could try and make that 200. And let's update the preview. And if I copy that to all the values, then you can see that we've now got a smoother transition of 200mm each time between the pitches that we've defined. If we were to try and enter a transition value which can't fit, so for instance if I try and set this transition value to, let's say, 1000 or something like that, then it's going to tell me, hang on, you don't have space for a curve that's 1000mm long there, there's just not room. So what it will do, if I hover over the cell, it should tell me what the maximum transition distance available is. You can see that's 550 something. So if I make that, let's say 540, then you see it will fit that curve in for me. That's this big curve here now. It's a curve that's 540mm in this direction. Okay, and now if you do want the smoothest possible transition between two different pitches that you've specified, we do have an automatic option for that. Let me reset all these values back to 0. Let's say we want the smoothest possible transition between our pitch of 50 and our pitch of 100. What we can do is right click here and make smooth, and then we'll get the largest possible spline that we can fit between 50 and 100, as long as it's centered over the actual point we've specified to make the change. You see the spline has to be centered over there, so it looks like 753 or nearly 754 is the largest possible transition. But then of course we wouldn't be able to put any transition in here. If I put in a transition of even 5mm here, it's going to say, hang on, there's not space for a 5mm transition here, because this spline goes all the way up to here. There's not even room to fit a tiny little transition in here because all the space is taken up. And you see here, of course, as well, that the preview won't update if we've got any invalid values in the table here. So we can set that back to 0. The minute we've got valid values, we get an updated preview. Of course, if we were to do it the other way around, if I was to set this transition value back to 0, so we've got all sort of sharp changes, and if I right click and say make smooth on this one here, where we're going from 100 to 40, make smooth, we don't get the transition occurring here, we get the transition occurring here on the next change of pitches. So the order in which you do these operations does make a difference if you're using the right click make smooth command. Last thing to say on this initial overview of the tool, we can delete rows out of the table, of course. We can right click and delete any row here, delete a row, or if we hit this minus button here, that will remove the last row in the table. So let's try if I right click and remove, let's say, this row here, delete row, then we've now only got 2 pitch changes that we're specifying, from 50 millimeters, then 40 millimeters, and then 120 millimeters. Okay, so let's maybe change this so that it's really obvious what's going on. Let's maybe make that 150, and you can see a bit more clearly exactly what's going on here. Okay, so if we put a pitch that's a bit more sensible in here, as I said before, if we are okay with the design that we've specified, we can hit OK here and save the current table that we've defined here. If we want to cancel out of this and discard all of our changes, we can hit this button and that will not save any of the changes in here. But let's say we want to save the current table that we've defined in here, and that will take us back into the main builder, which is over here, and we'll see that table then defined. It's only read-only here, we can't edit it here, and you see the preview here. And you can see these sharp edges that we've got, these sharp changes of speed that we've defined for the bottle here. We would of course probably want to define a bit of a transition for that. So if we wanted to do that, we can just hit the edit button here, go back in here, and we can see the transition value here. Let's just maybe specify a transition value of 50, and maybe we could copy that to all of them. Right click, copy value to all. So we've got something of a transition between the two there, and now if we accept that and go back here, you can see the transition values of 50 millimeters are there. We don't have that very sharp change in bottle speed or bottle pitch there. And as I showed you before, now we've got both a bottle pitch table defined here, but also the option of using the previous simple pitch definition. We can switch between the two. So if I toggle there, this is one way of defining the pitch with just a start and end value and a lead in and lead out, and this is the other pitch that we've got saved inside this part. So it will save the pitch table inside the part, and you can toggle between the two with just a click of the button. Let's just quickly build this shaft. We can just leave the default settings. Let's hit go and build this shaft in the current position with the current bottle pitch table so that you can see the finished result. I will speed up the video here. Okay, so this shaft's created in 2.5 minutes, and you can see the bottle following the route that we defined in the multi-pitch table. So we'll say no, we don't want to continue with another operation. Take a look at that shaft, and what we're going to do now is start on the worked example that I mentioned at the start of this video. We're going to see, rather than entering random values into the table, we're going to see how we could create a shaft with these precise bottle pitches as you move along the shaft. So let's create a new empty part file and we can get to work. Because I've got this specific requirement for particular bottle pitches as I move along the shaft, I think what's going to be helpful for me here, and you might find this useful for your own designs as well, is to maybe open up an Excel spreadsheet and make sure that we calculate the right values to input into the multiple bottle pitch table. So I know that I want a pitch of 63 millimeters for one revolution of the shaft, then pitch of 82 for one revolution, and then I want 2 revolutions of a pitch of 126 millimeters, and so on and so forth. So this is the design, but I need one more column of information to be able to input this into the app easily, and that is the distance along the shaft. So what I'm going to do is to use Excel to help me to calculate that. Obviously it's a very simple calculation, but I can just use an equation in here. So this is position in the pitch table editor. So the distance is going to be 0 at the start. Let's make this equivalent to this one. And then I need an equation in here. So after I've got a bottle pitch of 63 millimeters for one revolution, I'm going to have traveled a distance of this plus, open brackets, this times this. So that will be a distance of, let's copy this format again down here. So that will be a distance of 63 millimeters along the shaft, which makes perfect sense, doesn't it? Pitch of 63 for one revolution. And then I can copy this equation down, and then we get our other distances along the shaft. So after we've then had a pitch of 82 millimeters for one revolution, we'll have gone this far along the shaft, and then we do a big jump here because we've got 2 times 126, and then the final pitch change is at 539 millimeters along the shaft. And then actually, if we copy this one further down, this will be the total length of our shaft that we require to fit in all of these, well, this quantity of revolutions for these specific pitches. We need a 620 millimeter long shaft. Okay, so that's all the information that we need to enter into the table. So let's shift back into Inventor now, and let's hit generate on the app, and we'll just use that table for reference now. Let's just maybe adjust a value here to make this slightly more sensible. And we know that we need a length of 620 millimeters, so I'll hit enter on that. And then we can go and edit the table of bottle pitches by clicking on this button here. We're currently only defining with a start and end pitch as usual. And now if we take a look at the Excel spreadsheet, we know that we need 1, 2, 3, 4 pitch changes. So let's get all the values that we need, all the rows that we need in there. So we've got 1 pitch change at the moment, so we need 2, 3, 4. Okay, and then let's check what the values actually need to be. So the pitch at the start is 63. I'll see how many of these I can remember. 63, 82, 126. Okay, of course we don't get the preview update until we've entered all of these values in. 142 and 81. Okay, and then the positions that we want to change these values: 63, 145, 397. Can only remember 2 or 3 values at a time. 397, 539. Okay, and we're nearly there. We just have to enter the transition values, and for simplicity at first I'm going to right click, copy the value of 0 to all of the cells. Actually, let's set that one to 0 as well. Okay, and we've got the preview of the bottle root has now updated there. So what methods can we use to see whether we've entered these values in correctly and we're getting the bottle pitches that we actually want? Well, let's put Inventor on half the screen here and put Excel on the other half of the screen. And let's take a look at this here. So these text values inside the sketch are going to be useful for us here. We can see the first pitch 63, 82, 126, 126. And then we've got a second pitch of 126, and then a pitch of 142, and then a final pitch of 81. Okay, so those are matching exactly our calculations here. Another thing we can do to check, if I just make Inventor full screen again, is we can see down here the number of shaft rotations we have for each pitch change. So you can see that these are round numbers. They don't have to be round numbers, of course. If I change this to a different value, 135, you can see that's a precise calculation. So 126 is giving us exactly 2 shaft rotations here with those positions. Also, another indicator that we've entered the values correctly here is that we can see the info label down the bottom here is telling us that we've got exactly 6 shaft rotations. 1, 2, 3, 4, 5, 6, and those are represented by horizontal lines in the sketch as well. And also they're represented by these vertical lines, as this path would be wrapped around the shaft. Just a quick note on the transition column. We mentioned this earlier in this video, but just a reminder, at the moment we will get these precise pitches between the bottles that we're after from the Excel table that we looked at. If we were, however, to enter transition values here higher than 0, let's for instance enter some transition values of maybe 150, and then if I right click on here, so that's put a spline in there, you can see, but if I right click here and copy the value to all of them, then we've introduced these spline curves that are centered on the change of pitch point represented by each row in the table, and these curves of course mean that the bottle isn't precisely on top of the point that we've specified. So we've specified this point here, but because the bottle is in the middle of its transition here from one pitch to another pitch, it's not exactly on top of this point anymore, which means that when we zoom in here and look at the actual real world distances that will be between the bottles here, these are no longer the round numbers that we've specified for that reason. You know, they're not far out, but the higher we make these transition values, the bigger or the smoother we make the changes, the further out from the precise sharp values of bottle pitch we will actually be. Okay, so I'm going to set these back to all be 0, because in this case we're really not making massive pitch changes, and the fact that there's a sharp speed change for the bottles here on each of these changes is really not going to make too much difference in terms of the finished output of the shaft. The app will be able to calculate that just fine. It does actually put a tiny amount of smoothing and transition for a case like this anyway. So I'm going to say, yep, I'm happy with this bottle pitch table that I've defined. I can see that now here as a reference. Remember, as we said before, if I maybe save this part, let's just leave it as part 3 for the moment. Remember, as I said before, we can toggle back to the previous start and end pitch of 53 and 100. You know, let's maybe make that 180. Now if we toggle between the original pitch and the table defined pitches, you can see the difference there as we do the toggling. There's the pitches defined by the table, and if I toggle back, there's the pitches defined by the simple inputs here. Okay, so we want to go with the table defined pitches here, and just to finish off this exercise we want to perform a smooth build. We could do a rough shaft here. In fact, what we could do, what might be useful, is I'm actually going to run a simulation here before we create an actual shaft, and we can check the movement of the bottles. So if I expand the view of the data here of the bottles, we can see that the first bottle is on position 0. We can see the positions of the bottles here, which look very familiar based on our Excel spreadsheet, and these numbers here, the true pitch column of these bottles, also look very familiar, don't they? The double pitches of 126, 142 and 81. So this is the exact positions that we specified. Obviously this simulation doesn't show a finished shaft yet because we haven't built it, but we can see the data in there and we can be pretty confident that the finished result is going to be what we're after. So let's run the actual build after all this suspense. We don't need a lot of loft rails because it's just a circular bottle, so I'll just save the part and I'll hit build here with a single face for the shaft, and this should only take a couple of minutes because it's a very simple build with the circular bottle. So I'll speed up the video as usual. Okay, there's the shaft created in just over 2 minutes, so I'll say yes, I do want to continue with another operation just so that we can enjoy the payoff of the simulation of the finished shaft at the end. And I'll hit simulate. Okay, and there's the result. So you can see this looks a lot nicer with the finished shaft now, doesn't it? I'm going to hit the play button to generate those frames and then watch a nice fast video of it once I've got the 71 frames generated that I need in order to be able to play the video with a decent frame rate. Okay, remember we hit delete on our keyboard to stop the simulation, and if I put it on a nice fast speed by right clicking there, change it to 4 times speed and hit play, we get a nice fast video of the finished result. Hope you enjoyed the video and have an excellent day.